Hello everyone, welcome to the section looking at effective lengths and buckling. And this is a really key issue in steel design, understanding how do things buckle, because it significantly influences your design and the capacities that you calculate. And this, to be honest, is something that people in practice and all over often make mistakes with. And if you get something like a class 4 classification or effective area wrong, it's not going to kill anyone. It's not going to cause your building to be badly under or over designed. You might be 5 or 10% out. But if you get your effective lengths wrong, you may even either have half or double the predicted capacity. So this is a truly major issue in terms of real-world design. And I've seen cases going out to a 40-meter long billboard fixed to a building next to the N1 highway, where the billboard had actually started pulling off the building, and some of the members had started failing. And one of the issues of many was a lack of understanding of effective lengths and buckling lengths. So you just have to be very careful when it comes to effective lengths. Now, we're going to be going through some examples here, looking at how to calculate effective lengths. So on the screen, you'll see a truss, and we are now designing either the top or bottom chord. So we have the bottom chord we are designing there, and we have an equal angle, and I'm just going to use the axis convention in the red book. So there is my y-axis, my x-axis, my u and my v axis. V is weak, U is strong. And so now let's start having a look at how this will buckle. Firstly, the top chord. The top chord's quite straightforward because it's got a purlin there and a purlin there preventing any sideways movement. The member itself cannot buckle up and down because we've got these vertical elements here, and so it's restrained at this position and this position. So if I walk up to site and this top chord has failed, it'll look kind of like this. It'll move sideways, up or down or diagonally. It'll buckle between these two crosses. So whether I've got U, X or Y, K, L, U, V, X, and Y are all this sort of distance here. But now when it comes to the bottom chord, I've got a knee brace there and a knee brace there. So some diagonal member going down to the bottom of the chord, preventing sideways movement. And they stop any sideways movement there and there. And also, where do I stop vertical movement? Well, with these vertical truss element members there, there, and there. So when it comes for buckling about X, that's can it buckle up or down, it would look like that if I was going to consider this. Same thing with U and V. If U and V were to experience buckling, I'm just going to change color just to hopefully make it clearer for you. U and V, they would have to, the section would have to buckle both upwards and across to go diagonally up or down. So it would either have to go that way or that way to buckle about U or buckle about V. And so it can't go up, so it would follow the same shape. So it would buckle diagonally up or diagonally down to each side or the other. But when it comes to buckling about X, be very careful, because this is a horizontal movement into or out of the page. It is prevented moving there and moving there, but there's nothing preventing sideways movement at the midspan of those X's. So it will have an effective length all the way from there to there. So that is our KLX. Whereas all the other ones are these shorter lengths, KL, U, V, and Y. And this is the unrotated axis system. I'm not using Y prime, but I would use Y primed when designing the compressive resistance of the singly symmetric section. But now in terms of just effective lengths, there is it. It's my x-axis is double the effective length of the other one. And so be careful of that. So now moving on to sections. This is just, a quick wrap up on class 4 sections when it comes to the effective length and the effective length influence on sections, because we've been discussing class 4 previously. If you've got a section and if it is long and slender, what will happen is global buckling will happen first. So what you will have is when the effective length is long, global buckling will occur and you can use the total area of your section. If the effective length is short, this is as an example a class 4 1996 angle, then you'll have local buckling occurring. So a shorter effective length you have local buckling, longer length you have global, and so just be careful. That's also the effective length does influence whether local or global buckling occurs. So global, once again, the entire section would buckle between supports, like that, whereas local buckling, my angle would just experience a little buckle along its length. I've drawn that really badly, but I would have a local buckle, for instance, on my angle there. Something, part of the section would fail. Here we have a beam that has both axial loads and compressive loads on it. So let's start thinking, how would this buckle if we loaded it and loaded it and loaded it until it fails, and now we walk up to it on site, and what would it look like after it has failed? Firstly, look carefully at all those little X's where it says point of lateral support for flange. Now, what is that? Well, think about it this way. Imagine if there was a floor on top of this section, a steel grating or fuss trap, which is a steel plate, and the floor sitting on top. And this floor is connected to other beams, and it forms a sort of rigid system on top of it. It prevents sideways movement, especially we fix the floor there, we fix the floor there, and we fix the floor there to the beam. When we load this steel grating, let's say, we load it up, it will move up and down with the beam. So as we load the floor is carried by the beam will go up and down, and so the floor will go up and down. However, if the beam tries to buckle laterally, this floor will stop it from moving sideways. So there is a lateral support where the floor is fixed to the beam. And if this, for instance, was continuously welded, you'd actually have basically a continuous connection between the floor and the beam. So a lateral support is something that moves with the beam, but it prevents sideways movement. So a lateral support, if it's a support like here, this prevents both sideways movement and up and down movement. But a lateral support only prevents movement sideways. Normally it's a purlin or girt or flooring or another part of the structure, so they all move together, but they don't prevent moment. I mean, yeah, so for instance, my lateral support here doesn't carry any of this force. This force is carried here and here. My lateral supports do not influence the bending moment diagram. So the shape of the bending moment diagram for this beam doesn't matter if I have 1 lateral support or 50 lateral supports. The bending moment diagram is the same, but buckling is very different. But coming back to buckling, if we walked up into the structure on site, we load it and we load it and load it, eventually it gets to edge, oops, I'm going to fail now, and it can't move upward there, it can't move upward there, it can't move upward there, and it would look like this. If we looked at it from the side, it would look like that. So our effective length, Lx, is this length there. And what also happens is our L, so we would see this, it would physically look like this on site. It can rotate at these positions. So our effective length would be K is 1, or Kx is 1, because it's pinned in all these positions. It can rotate. But now when it comes to buckling about y-axis, it can't move horizontally at any of these positions. So what will happen is we end up with lateral supports here, all the way down, like that, etc. And we have this sort of sinusoidal. So if I was looking down on this beam and we load it and load it and load it till it fails, it would fail between points of lateral support. So our Ly would be like this, and once again we'd have a Ky of 1. Now, what about torsion? What is torsion? Firstly, hopefully you all know by this stage, but you've got a beam. If I have a support there and there to it, I've got a floor fixed to the top and a beam to the bottom, or I've got a beam connected into the side of it which prevents twist. You don't need very much. If you just have, for instance, 2 little bolts, you'll prevent torsion. Now, this will have a torsional restraint. This won't. So when I have a look at this, this will now rotate like that. And so when it comes to a torsional length, let me just use another color actually so you can see the difference between the y-axis and a z-axis. there's torsion, and I will have torsion length like this. It'll actually twist along its length, so you wouldn't really see it. It would literally twist. It would twist between there and there. So it would twist between there and there, and it would just wind itself up in a little knot along its longitudinal axis. Because at this position here, it's not perfect torsion. Pure torsion would be sort of twisting about the center of it. So this is not 100% torsionally free here. If we test in this lab, depending on what is here, it might be some amount of restraint. I'm conservatively assuming that if the section can twist, there's no torsional restraint. But if this was a short squat column, we may actually find that just one point and the stiffness around it would be enough. But for sake of safe calculations, I've assumed that if there's only a single small point at which it's connected, it's not torsionally restrained. If there is more than one point, even if it's two little bolts, then it's torsionally restrained. So let's go on to this one, and I'm going to go through this one much quicker now after we've gone through everything. We've got a fixed column. There is now, let's say this axial load, it's part of a frame, and now there's axial load acting on it as the entire structure tries to move. And we've got purlins on top. The purlins carry some sheeting, so there's some sheeting there. That is not drawn, but the sheeting is carried. And now we've got a knee brace. So I've got various positions at which this section cannot move sideways. But in terms of moving up and down, this sheeting and these purlins will move with the structure. So here it'll be fixed, here it'll be fixed. Everywhere else it'll just be fixed and fixed. So fixed and fixed. And a Lx of the full area. Buckling about Y, if it was to move sideways, it's fixed there, and then we will design between points of lateral support always. So if I was actually designing this as a column, I'd have 1, 2, 3, 4, 5, 6. I would design this as 6 columns. But I'm an engineer, I don't want to do 6 times the amount of work. I would pick the worst case. The worst case would be where the force is the highest or the resistance is the lowest. And so where the resistance is the lowest would be the longest effective length. Ly, because it's pinned, pin, longest effective length. See, that's fixed pinned, and a slightly shorter length. So this would be probably my worst case span between C and D, or well, BC, CD, DE. They're all the same, these sort of 3 sections, and even actually E, F, but to be honest, this would virtually form a fixity here because these are so close together, it'll virtually form a fixity. So one of these 3 spans would probably be worst case. And then same thing, my torsional length, I would probably take between B and E if I need to have a look at that. Now, let's have a look at another structure. Here we have a little hanger of sorts, a funny looking little structure with a point load on the end. And if it was braced, it means that I have bolted this to the building next door. And if it's braced in the weak axis, I've got something there that's preventing horizontal movement. The rest of the structure, or it's fixed to something, there's something preventing movement at that position. And now think about what will happen, what will it look like as it fails. If it buckles about the strong axis, it can rotate there. It's fixed at the bottom, so the entire deflected shape would look like this. So on Lx would, but now we've got a fixed pinned connection. Same thing with this, fixed pinned, and then our Ly would be this. So this would be in plan. Sorry, I'm just going to show you. There is my buckling about X and buckling about Y axis. This is a PC, a parallel channel 100 by 50, so it's a little channel support. And now, what happens if it wasn't there wasn't that bracing? If it was just a freestanding element, looked like so, and what would occur? And so you would end up something like this. It would lean over, the entire structure would just lean over sideways. Could lean one way or the other. So now what you have is our length is the same, our L, X, and our Ly, but our effective length becomes much longer because our K is a fixed free condition. So depending on your code, this is normally about 2 kx, ky, and so you end up with a much, much lower capacity. And so, because here it was about 0.7 fixed pinned, here it's about 2, so you end up with a much lower capacity depending on can it move sideways there or not. Okay, hopefully that's given you an overview of effective lengths and applying this to structures. Thank you.